Assalamu alaikum. This is lecture number 5, Physics 731. I'll talk about orthogonality and normalization of Bessel functions, and then Bessel functions with imaginary arguments. Now let's talk about the roots of Bessel functions. Here down, this is j sub 0. We are looking for j sub nu. Nu is the order of the Bessel function of x nu n is the roots, n runs from one first root, second root, third root, and so on. This is an example of j sub 0. This is the first root, the second root, third root, fourth root, and so on. It looks like a trigonometric function. This is some roots for nu equal 0, for nu equal 1, and for nu equal 2. Now, knowing that, we can show that square root rho j sub nu of x nu sub n rho a form a complete set, where nu is the order of Bessel functions, which is fixed, and n is the roots of that order. Rho varies between 0 and a. Now, if we substitute j in Bessel equation, we have this form. Now I will multiply this equation by this integral 0 to a d rho of rho g sub nu of x nu n rho n prime. This is n and this is n prime, and integrate by parts. Integration by parts for the first term, we have this is u and this is dv. Integration u dv gives u v minus v integration of du. So the first term is this one between 0 and a, which is at a 0, because this is a over a is 1. We have x and n prime. At 0, we multiply rho 0, multiply 0 by this thing gives you 0 minus v du. We get this term. You have to be careful about n and n prime, plus the integration of the last term. Now, in this equation, I will replace n prime by n, and n by n prime, we get the second equation, and then subtract. So we get this equation. Subtraction gives this equation. Now, to evaluate this equation, we use recurrence relation, and it's equal to this thing, a square over 2 j sub nu plus 1 x nu n square delta n n prime. Either this equals 0 or this equals 0. This is the orthonormality condition for the Bessel function. So rho square root rho j sub nu form a complete set of function. This is the summary of what we have done above. Now, any function f of rho defined in the interval 0a can be expanded in terms of this function of j sub nu. We can write f sub rho as a series from n equal 1 to infinity, a sub nu n, j sub nu x nu n rho over a. To find the constant a sub nu n, we multiply this equation by integration 0 from a from 0 to a d rho j sub nu x nu prime. Here we have n, here we have n prime rho over a, and then evaluate the integral on the right hand side using the orthonormality relation. We get this expression. Finally, we have a sub nu. When n equal n prime, you have to run the sum. One of them is equal to n prime. We get this expression. So a sub nu n prime is 2 over a square 1 over this thing times this integral. You have to know f of rho in order to evaluate this integral. Now let's go to Bessel function with imaginary argument. In the Bessel equation, we have to replace k by I sub ki is root minus 1. Doing so, we get this equation. d2r by dr squared plus 1 over rho dr by d rho minus of k squared plus nu squared over rho squared r. We know that k rho is equal x, so it reduced to this form. Now we get a new, this is a Bessel equation, but with a new, but the function is with an imaginary argument. We call it the solution modified Bessel functions with or Bessel functions of a pure imaginary argument. We call it I. The relation between I and nu, you have to substitute in g of a nu ix instead of x. We get this thing I to the power minus nu j sub nu of x. For the second solution, we have k nu of x equal pi over 2I to the power nu plus 1 h sub nu to the power 1 I of x. Now the behavior of this function for small arguments for I for nu is given by this expression, and for k nu is given by this expression. For large values of x, asymptotic behavior is given by these two expressions. The first one for I sub nu and the second one for k sub nu. Now let's apply an example. Here we have a cylinder, empty cylinder. The potential at z equal 0 is 0, and at rho equal a is 0, and at z equal l, the potential is given by some function that depends on rho and phi. Now, the solution, the phi solution is, we call it q, which is a sine m phi plus b cosine m phi. Along the z solution is exponential plus or minus k z. We know that as z equals 0, this is 0. So if you put z of 0 equals 0, you get t equal minus c. That's the solution is hyperabolic sine of kz. Now for the q, it's better to use the exponentials a to I phi nu phi plus b a to minus nu phi. And then here for phi to be single value, it leads to m must be an integer. Now we have this is the phi solution. This proves that m must be integer. You can see it from here. And then this is the radial part. Phi is finite as rho equal to 0. Newman function is divergent, so we have to take d equals 0. Then we left with r of rho equal some constant time g sub m. Now we also have phi at rho equal a at the surface of the side surface of the cylinder equals 0. This means that 0 equals c j sub m k m n a. So we are looking for the roots now of the Bessel functions. K sub m n equal at x m n over a, where n equal 1, 2, 3, etc. Now put this three solution in phi. We have to sum from m equals 0 to infinity, from n equal 1 to infinity, j sub m, n, km, and rho, hyperabolic sine. This is the z part times the phi part, which is a combination of sine and cosine. There is only one, we left with one boundary condition, which at z equal l, which is given by this function, v of rho phi. Now, in order to find these constants, we have to apply this boundary condition. Doing so, v of rho phi at z equal l, we get this term times hyperabolic sine k sub mn times l. Now z equal l times the combination of sine and cosine. This is called Fourier series and Fourier Bessel series. Now to find the constants, first we multiply from left by sine L phi d phi between 0 to 2 pi and 0 to a d rho g nu k m and o to, m and rho to use the orthonormality of j and the orthonormality of the sine L phi. And then for the second constant we multiply by cosine L phi rho g sub n km and of rho. Of course we have to integrate. Now doing so we get for am and this expression. This is hyperabolic sec. It's 1 over hyperabolic sine. B sub mn is given by this expression. Now this is here I'm repeating these calculations just to show how we get A sub mn and B sub mn. Once you know V, you can perform these integrals. Now the second example is to let A goes to infinity. In this case we are the summation over n goes into integral, and if phi is finite, then for in charge free space, no charge, for z positive, then phi as z goes to infinity is equal to 0. Phi go to 0 as z equal to infinity. So the previous solution, this one, V with AM and ABN is given by, reduces to this form, summation over n from 0 to infinity, integration from 0 to infinity dk times e to k minus z. Exponential a k to plus z is now divergence. We get rid of this, times the Bessel function times the linear combination of sine and cosine. Now if we assume that phi at z equals 0 in xy plane is equal v of rho phi, that's phi is given in xy plane, then this equation z equals 0, we get v of rho phi equal this integration. Again, to find a sub m of k, now k is a continuous variable, and b sub m k, we have to multiply both sides from 0 to 2 pi, the first term by sine m prime phi, the d phi, for the pm we multiply by cosine m prime phi prime, and using the orthonormality. And notice that the orthonormality for the Bessel function now becomes from 0 to infinity xgm of k xgm of k prime x dx equal 1 over k Dirac delta function k prime minus k. So once you perform these integrals, we get a sub m of k bm is this expression. The upper term is for a sub m, and the lower term, which includes cosine sub m phi, is for b sub m. But we have for m equals 0, this is 1, this is 0, we have to replace b by, divide b0 by 2. This is from Fourier cosine series. That's all. Thank you.